While we're getting set up, I'll introduce the next speaker. Keltin joined the Software Engineering Institute's AI division in June of 2023 as an assistant machine learning research scientist after graduating from Carnegie Mellon University with a BS in statistics and machine learning and a major in computer science. His previous research projects have included work on machine unlearning, adversarial attacks on machine learning systems, and machine learning for materials discovery. Please help me welcome Keltin Grimes to the podium.
Okay, great. Thanks. All right. To present my team's work on validating fuel savings for aircraft fleets using in-flight data recordings. Okay, cool. Okay, so this work was done with me and Kevin, who's here in the audience, at the Software Engineering Institute. We're at FFRDC, part of Carnegie Mellon. So kind of an overview of the project. The general goal here is how do we validate whether upgrades to aircraft are actually saving us fuel? Kind of alternatively, how do we know if something's gone wrong with a software update? And kind of successful solutions here can have a big impact. You can imagine saving like 0.5% or 1% fuel over a fleet of aircraft can save a lot of money for someone like the Air Force or even commercial fleets. And so the end goal of kind of this line of work as a whole is to be able to detect interventions with as little as a 0.5% fuel rate reduction. And this will sort of inform decision-making at the Air Force. And yeah, so this work was done for the Secretary of the Air Force's Operational Energy Division. So just to give you all an idea of what we're talking about here, interventions can be pretty general. All you need is a date and a tail number, which just says when a certain aircraft received the intervention, and then that lets you tell which sorties do and do not have the intervention. So an example on the right here, a vertical pallet stacker, that's more of a operational intervention, which allows them to store more cargo on like a C-17, for example, or here on the bottom right, are some micro vanes that reduce drag on the aircraft. Okay, so the first challenge when you're working on this is the data. So if you're looking at different fleets of aircraft, the different aircraft types have different flight characteristics that you have to deal with. They have different sensor suites, might come in different data formats. And so data cleaning here was one of our big time bottlenecks. An example on the right is a sortie from an A-10. And on the bottom is the gross weight of the aircraft jumping up and down rapidly, about 25,000 pounds, which is obviously not accurate. So that's something we just have to kind of throw away because it's an unrecoverable error. But so if you're thinking about implementing this sort of thing at a production level, you're going to have to think carefully about how you design the data processing so that you're maximizing code reuse and minimizing the time to bring on new fleets of aircraft. We did find throughout the project that the models are fairly robust to noise, so you don't have to do too much cleaning, but it does seem to help. So the next thing we do once we have some relatively clean data is we segment the sorties into different sections of flight. So like taxi, takeoff, landing. An important one is cruise, where the plane is flying quite steady. And this kind of minimizes the variation in the data we have, lets us have a cleaner signal of what's happening. So we'll often focus just on cruise segments when we're trying to detect the effect of an intervention. You can also imagine that some interventions might only apply to a certain type of flight, like maybe it only something with landing gear, for example. So you are going to want to zoom in on the landing of a sortie. So this can be another time bottleneck when you're developing this. Our solution was that we have a set of heuristics to do this segmenting, but we have parameters that you can adjust. So if you're looking at like a cargo aircraft versus a fighter jet, one might have a higher cruising altitude than the other. And so you can adjust the parameter there to say, we only consider segments of flight above this altitude to be cruise segments. Then you can adjust the parameters and get a segmenting heuristics that work for that aircraft type. I'm gonna skip this slide. Okay, so then the next problem you run into is that you have almost no actual real world intervention data. And so if you're developing these models and trying to evaluate their performance, you need to simulate it. So there's a lot of things you could do here. We took a relatively simple approach where if we're looking at an intervention of size n, then we're going to randomly select some tail numbers and take the n most recent sorties from that subset. And then we reduce the fuel rate by some percent shift sampled from a distribution to add a little bit of noise. Other things you can imagine doing is taking into account like bases or aircraft locations, because maybe an intervention is applied at one base first, tested out before it's applied to the entire fleet. There's other more complex things you could do. You can imagine simulating an aircraft to see potentially how an intervention is affecting things, but that's what we've done for this project. And then on to the modeling. So the first step is that we fit some model of fuel rates without knowledge of the intervention. So we have features like altitude, aircraft speed, pitch, yaw, and then we predict the fuel rate. We mainly looked at linear models and XGBoost models, which is a tree-based method, which we found to generally work a bit better than linear. But you could imagine other models, more or less complex. So you have this model, and then you get the residuals on the sorties. And so what you would imagine is that if an intervention is working, your model is going to be overestimating the fuel use of the sorties with the intervention. And so you'd imagine that you'd see a difference in residuals between the non-intervened sorties and the intervened sorties. And then you would do a t-test to see whether if they're significantly different. To generalize this to multiple interventions on the same fleet, you do it like a regression over indicator variables for each intervention. So those are our models. And now we'll get into results first on our simulated data. So on the left is the A10s, which is the first data set we looked at, which was very messy and not a ton of data to work with. And then on the right is F-15s, which the data was actually quite clean. So the numbers here are pretty small, but on the bottom is the number of sorties with the intervention, going from about 10 to 1,000. And then the y-axis is the percent fuel that's being saved in the simulation. The bottom being no savings, going up to about 0.5%, 1%, up to 10%. And so you can see, at least with our simulations, that for A10s, we can reliably detect interventions of about 4% fuel savings. The green is basically the accuracy over multiple trials. In the F-15s, we actually get down to around 1%, a little bit into 0.5%, but then also on this bottom row, which is a null intervention, it's not actually saving any fuel, you see that there's actually some false positives. So you might want to adjust your decision threshold so you're not getting false positives, depending on what you care about. Then in terms of real world results, unfortunately, only a sample size of 1 here, but we did get engine wash data for the KC-135 fleet going back to 2013. The subject matter experts we talked to said that we should expect about a 0.5 to 1% fuel rate improvement. So we ran our models on about 54,000 sorties between 2021 and 2023, of which 2,500 had the intervention. And so we trained our models and we found that the coefficients were basically right in line with the SME estimates, and the models were quite confident that the intervention was working, which was encouraging. So then one issue we ran into was p-value calibration. So if we repeatedly simulated the null case where the intervention's not actually doing anything, we found lower p-values than expected than what you would expect if your model was properly calibrated, meaning that it was overconfident. And so this plot on the right, the blue line is the perfect calibration case. This is like a log plot of the p-values we saw versus what we'd expect. The red is what we saw with these simulations. So this is presumably due to some dependence that our models aren't taking into account, likely the tail number, because there's likely sorties from the same tail number are probably fairly related. They're not independent samples. So these red points are linear, so it's pretty easy to calibrate them if you want to. But there are some caveats with this. One, this calibration is dependent on having accurate simulations, which a lot of our results are. But the other thing is that the models seem to work pretty well without the calibration. So if you do calibrate it, then you're never going to detect anything because you're not very confident about anything. So the sort of alternative view you can take is to look at this in terms of precision and recall, kind of throw the uncertainty estimates and p-values out of the window, which is kind of a trade-off, but then you aren't worried about calibration and are just sort of saying this is how well our model performs in terms of precision and recall. An advantage there is that if you have decision makers, they can kind of tune these thresholds depending on what they care about. So gonna talk about this, which is a little interesting. So one of the things that kind of felt funny to us when we were doing this is that you're kind of coming into it without any prior on what you're doing, but you would imagine that if you're doing a huge upgrade to a fleet costing millions of dollars, hopefully there's more than a 50% chance of success of your intervention actually saving fuel, if that's what you're aiming for. So if you do a little bit of math and you assume a probability of alpha that your intervention is saving you fuel, then it turns out all the other metrics except precision stay the same, and then you get this little formula for your precision adjusted by your prior. And ultimately, it says that if you have a strong prior for it being successful, and then the model says that it is successful, then you can actually be very confident about it actually being successful, which kind of makes sense. Have some examples on the right of a simulation we had where the recall stays fixed depending on your prior, and as you're more confident, your precision goes up. So last thing I'll talk about is some initial look into causal modeling. So another thing we were thinking about throughout the project is, well, we have these models, but they're not really allowing us to say that this intervention is causing a fuel rate improvement. And then another thing is that we have these engine features like engine temperature or engine oil pressure, or oil temperature, which are really highly correlated with fuel rate. And we kind of have this intuition that if an intervention is causing a fuel rate decrease, it's probably also causing a decrease in engine temperature, say. So if you include these in your models, then you kind of have that causation built into your model. And so it's kind of going to soak up the effect of your intervention. And so then when you go to model the intervention, your model is going to already account for it. And so it's going to kind of mess up what you're doing. So we looked into this a little bit towards the end of the project. We were looking at Granger causality in quotes, because it actually doesn't tell you anything about actual causality. It's just saying that for time series, one feature predicts another feature in the future, which can be an indicator of causality, but isn't necessarily. So we find these correlations between the features in the sorties. We filter out the low correlations, filter until we get a cycle-free graph, which gives you something like this, which can be sort of odd because you have things like lateral stick force, longitudinal stick force. You might imagine that those should kind of be at the top of the graph because the pilot is moving the stick, and it seems like they're causing the plane to move. But at least when we do this analysis, we find that they're not, and longitudinal stick force is actually at the bottom, and you see a lot of variables causing altitude. So that sort of is what it is. But so that was our kind of first foray into causal modeling. But to do this sort of properly, you really need good subject matter experts to kind of understand, kind of build this graph for you in the first place.